All right. Good afternoon. Today I'm gonna work on some more uh, examples on multi-loop mechanisms where you need to have more than one loop to distribution analysis. Then tomorrow we are gonna start velocity analysis, which is chapter 6. I will post the new homeworks tomorrow, which is due in 2 weeks. So the due date for the homework 7 would be October 24th, the day that we have exam. So this is another mechanism that we would like to do displacement analysis on that. Let me draw that mechanism on the board, then we are going to do the class activity to find the number of links, number of joints, label them up, and form the vectors, and then see how many loops we need. Alright, we have this mechanism. When you are given with a mechanism, first you need to find degree of freedom. To find degree of freedom, you need to find number of links, number of joints. Then label the links and angle. Before label the angles and vectors. First we need to form the vectors, not vector loop, just vectors. After you form the vectors, each link should be assigned by one vector. So label the angles for the vector loop. The question. So for this mechanism, let's see how it's gonna look like. If we want to find the degree of freedom, we need to find the number of links, number of joints, then label the links, joints. To label the angle, you should form the vectors. So for each link, assign a vector, then we can start from that point. Any question about this class activity? Okay, work on this, then I call. Number 28. Would you come to the board and just, for this step, just label how many links and join can you see there?
Like what is the model?
Yes. One is always ground. It has been welded, so there is no joint.
Okay.
Thank you.
C is not a joint. C is not a joint.
It's been welded. So number 36. So she believes that we have 7 joints and 7 links. Number 36 is not Jeremy. Jeremy is not. number 26. No? Number 20. Michael. Number 1. I know. Yeah,
But, you know,
that's fine. Your 6 is the ground. So n equals to 6, f1 equals to 7. Any different out? So the only difference between these two is number of links. Julia just count this as an individual link, which is not, because there is no, the definition of the link is a rigid body with at least 2 nodes which can be connected to the other links. This part has only 1 node. It's basically part of this link, so we should count it as a separate link. But the rest is correct. So 1 is ground, 2 is this link, 3 is this big guy, not 4. The slider is 4. This is 5, this guy. And another slider that we have is number 6.
so
No.
that C is a third user.
C is the part of B, D. So this is the rigid body, the entire of that. So because if I add 1 joint here, I should count it as a separate link. If I put a rotational or translational joint there. But right now it's going to be a part of this guy. So 1 joint here, number 2, number 3 and 4. 3 is rotational, 3 rotational between the slider and this guy. 4 is, 3 is translational between the slider and this guy. 4 is rotational between ground and this guy. 5, 6 and 7. 6 rotational between 5 and 6. 7 is translational between ground and a slider. So number of links is 6, number of joints is 7. M would be 3 times 6 minus 1, 5 minus 2 times 7. 1 degree of freedom. So we have 6 links, 5 moving links. 1 is ground. Out of 5 moving, we have 2 sliders. It means 2 variables should be distance, and 3 out of 5 should be angles. So 3 angles, 3 rotational plus 2 translational. So I'm gonna start from the origin, which is this one. I put the arrow at this direction for this. For this big guy, I put the arrow at point B. For this one, I put the arrow right here. For a slider, the distance of the slider from the ground, I'm gonna define that as a S, this distance. And from this point, the offset between the slider and point A in the horizontal direction, I label this as A. So A, B, C is this small, D would be this big guy, E is this distance, F is this distance, what else? And G is going to be the distance between A and D. So A, the offset of the slider from the origin in horizontal direction. S would be the distance of the slider from the ground line. And we continue B, C, D, E, F, and G. So now I can label the angles. I should be able to define 3 angles. For link 2, I have to define angle of theta 2 at point A. Theta 2 can be defined here. For this link, link 3, 1, 2, 3. The angle of theta 3 should be measured at point D because the ending point is point P. For this guy, I should measure the angle at point, whatever is this point, it's theta 5. So the variables, 5 moving links, 5 variables. 5 moving, 5 variables. Theta 2, theta 3, and theta 5. S for this slider and D. D is varying while the mechanism is moving. So I'm done with what a number of degree of freedom. I could label the links and the vectors, and I could label the angles. Then I count the number of, let me write the nouns, A, B, C, A is constant, B is constant, C is constant, D is varying, E, F, and G. This distance is constant, G is constant. And constant. Nouns are constant, degree of freedom is 1, theta 2 is given. Theta 2 is given. I remove theta 2 from the unknown, from the variable. I should be able to solve for unknown. Theta 3, theta 5, E, and S. So 4 unknowns. 4 unknowns. It's gonna tell me I need 2 loops. Because each loop can solve for 2 unknowns, I need 2 loops. Loop 1 must include theta 2, and it should be, we should be able to solve that mechanism. So I go with this mechanism, this one. So loop 1 must have theta 2, and it should be a mechanism that we can solve for that. I'll go from A to B, B to D, and back to A. A, B, D, A. So vector loop. Vector loop equation. B is the point with two vectors ending to that. B is the point. There are two vectors ending to that. AB, I'll reach to point B, I'll stop here. I'm moving from A to D, D to B. So in this vector loop equation, theta 2 is given. I'm solving for theta 3 and G. So variables are theta 2, theta 3, and G. Constants are B, D, sorry. B and G are constant. This distance is B, this is G constant, but D is variable. So now will be theta 2 plus constant. We are solving for the remaining variable, which are theta 3 and D. This vector equation is telling me B cosine of theta 2 equals to AD. A to D. A to D has the distance of G. Cosine of 0 is going to be 1. So dB would be D cosine of theta 3. And D sine of theta 2 is D sine of theta 3. There is no G term. Any questions so far? So we got two equations. We are solving for theta 3 and D. You can, yes.
Since this is a triangle, why didn't we just use cosine rule? Like we could get both the angle and the distance.
We can. I was going to talk about that as well. For this specific case, you can use the cosine rule on the triangle, but you get the same results. So I just want to show you. I'm not gonna do the process for this. I'm gonna use the cosine rule on triangle, but this is the standard form that I'm suggesting that we follow for any mechanism. We can eliminate theta 3 by keeping theta 3 terms in one side, move G to the other side, square, add them up, get rid of theta 3. You get equation as a term of D squared, solve for D. But in this triangle, if you look at this triangle, we are looking for D. So write the cosine rule for this guy. D A square would be B square plus G square minus 2 BG cosine of theta 2, cosine of this angle. So if you do the math for this one, you end up to this equation. Cosine rho. So if you have triangle, maybe it's better that it's easier to use the cosine rule just to simplify one step. And after you find D, you can either plug in here, find theta 3, one set triangles here, triangles there, find the matching pair, and we get D and theta 3. Now D and theta 3 are given. We are going to go to the second loop to solve for S and theta 5. Any questions so far before we go to the second part of the problem? Now we are done with theta 3 and D. I should solve for theta 5 and S. I should find a loop which has theta 5 and S and that. So I'll go with this loop. A, B, C, E, F, G and A. So loop 2, A to B, B to C, C to E, E to F, F to G, and back to point A. Starting from here, going in this direction, back to point A. This loop has theta 5, it has S on it. So now write a vector loop for that. For the distance that we don't have vector, just for the loop. So for this part, I don't have the loop, I don't have a vector, just consider this as a vector, and this one as a vector. Let's remove this direction. Something like this. So point 3 has two vectors and that. I can write the loop AB. I stop here. I'll go through this direction. AG plus GF, AG plus GF plus FE. For this part, I need to have define one vector from E to C. EC plus CB. C summation of this vector, it's gonna give me AB. AG ending should be the same. AG plus GF, AF. And the second letter is the same as the first letter. AF plus FE is gonna give me AE. E and E is gonna give me AC. C and D is gonna give me AB. This is how you can double check your vector loop equation. Now try to write the vector loop equation in x component and y component. AB, it's a B cosine of theta 2 equals to AG. AG has the distance of A, it's constant, cosine of 0, because the angle with the ground is 0, I will get A times 1. GF, the angle is 270, or you can say there is no distance in X vector. I'm just writing S cosine of 270 degrees, but I know that it's going to be 0. F to E, the distance is F, the angle is theta 5. Now E to C, I need to know what is this angle. You should know that since this part was this guy was a part of the rigid body of BD, this angle is not a new angle. It depends on theta 3, which is this angle. This is 90 degrees. This angle equals to this angle. This is 90. So theta 3 minus 90. Yes, the summation of these three is 180 degree, 90 degree plus this angle plus this is 180 degree, and this is going to be 180 minus theta 3. Subtract from 90, it's going to be 93 plus theta 3 minus 95. So this angle is gonna, you can find it theta 3 minus 90. These are some tricks that you need to do to find the correct angle. So the length is E cosine of theta 3 minus 90 plus this part, which is constant, angle is theta 3. This angle equals to this angle. So for the y component, just change cosine to sine. A doesn't have any y component. S is going to be sine of 270, which is not negative 1. F sine of theta 5 plus E sine of theta 3 minus 90 plus C sine of theta 3. We get two equations. In two equations, the only unknowns are theta 3 and S. Sorry, theta 5 and S. B is known, theta 2 is known, A is known, S is one of the variables. This term is gone because S cosine of 270 is 0. F is known, theta 5 we are looking for. Theta 3 is coming from the first loop, and theta 3 is coming from the first loop. Same thing for the second equation. So we are solving for theta 5 and S. Yeah. What you can do, you can get rid of theta 5 first, move every term which is now to the left side. E cosine of theta 2 minus A minus E cosine of theta 3 minus 90 minus C cosine of theta 3 equals to F cosine of theta 5. All terms on the left side is noun. I just labeled that as an M to simplify the notation. M would be F cosine of theta 5. Same thing here. Keep F sine of theta 5 in one side. This is unknown. with the other terms move to this other side. B sine of theta 2 minus E sine of theta 3 minus 90 minus C sine of theta 3 minus S sine of 270. Sine of 270 is negative 1. Minus S times negative 1 is going to be positive. Equals to F sine of theta 5. So this part is now, I define n as an intermediate variable. N plus S equals to F sine of theta 5. M would be F cosine of theta 5. A square add them up. Right hand side you will get F squared cosine squared theta 5, F squared sine squared theta 5. You will get F squared. Left hand side you will get M squared N squared plus S squared plus 2 NS. It's a quadratic equation. S squared plus 2NS plus M squared plus N squared minus F squared equals to 0. Solve for S. Solve for S. After you find S, back to this equation without S squared. Solve for theta 5. Theta 5 is going to be sine of theta 5 would be n plus S divided by F. And here cosine of theta 5 is m divided by f. Two angles coming from cosine, two angles coming from sine. Find the matching pair.
Question. So we would only take the positive value for F.
Again, if you are looking for two nodes, you have to use gross value. If you just want to work with the one node, then take the positive value.
If we have something like this on the test, will you ask us to find do it for both nodes?
I'll tell you on the key point on these types of the problem. The things that I'm looking for this type of the problem, how you can set up the equation, set up the vector loops, how many loops do we need, and find the number of variables. Yes.
So right after the quantity of n, it says like plus s something, I can't read that.
This
Yes.
that was negative s minus sine of 270, which I changed it to positive, equals to f sine of theta 5.
Okay.
I kept this term in one side, moving the other term to the other. There are any question about this example? There are on this slide. There are some other examples where we need to have multi-loop. I remember I gave this problem as a take-home exam to one of the, it was 2 years ago. There were 3 problems on the exam. One was take-home exam. They have to, because I cannot ask in the exam to do it in 15 minutes. So I asked them to do by at home and submit it.
Next week we haven't taken that class.
I have not designed the exam yet. So I had some other problems here if you want to practice. One of the homework problem which is due tomorrow, the last one, is similar to the example that we this problem was one of the one of the exams problem that I had 4 years ago or 3 years ago, I'm not sure. So that the idea was simple. So we have this slider crank. A slider crank that you have seen, it was either no offset like this or offset in vertical direction. So what if we have something like this? Slider crank with the angle. The idea would be the same. The number of links is still 1 ground, 2, 3, 4. Number of joints 1, 2, 3 rotational, 4 translational. So 4 links, 4 joints, and degree of freedom is 1. For the vectors, for this guy I put the arrow here. For this guy I put the arrow there. From here to this point I have this guy and this guy. If this is point C. Now write the vector loop equation. If this is O, point A is the point with 2 arrows and into that. OA would be AC plus CB plus EA. Again, when you write the vector loop, both sides should end up to the same vector. The second letter of the vector should be the same as the first letter of the next line. So OC plus CB should be OB, OB plus BA is going to be BA, or OA. So X component of OC is fixed. Suppose if this is A, this is B, this is C, and this is S. C is constant, so it's going to be C cosine of 0. CB would be S cosine of 60 plus BA. B cosine of theta 3. And right side is going to be A cosine of theta 2. Second equation is going to be A sine of theta 2 equals to C sine of 0, which is 0, C sine of 60 plus b sine of theta 2. Two equation, the unknowns will be theta 3 and s. S. Not true.
No, this would be.
Yeah, thank you. We are solving for these two. First, get rid of theta 3, solve for s, then solve for, back to this two equation, solve for theta 3. Good? How can I do that? Just move these two terms, a cosine of theta 2 minus c minus s cosine of 60 equals to b cosine of theta 3. And a sine of theta 2 minus s sine of 60 equals to b sine of theta 3. Let's square them. If you square and add them up, you can get to that theta 3. Right hand side will be b squared. Left hand side, you will get some terms of s and some noun terms. So the only variable will be s. You will end up with a quadratic equation and solve for s. Any question on this? This is the last example that we are covering for displacement analysis. Tomorrow we are gonna start velocity analysis, which is about deriving the vector loop equation. We are differentiate these two equations with respect to time to get the velocity equation. Alright, we continue tomorrow.